we are going to be talking about simple harmonic motion. And do you remember what simple harmonic motion means? Good. What is the simple part? Yeah, it's a kind of harmonic motion that can be defined using a sine or cosine function. So we're going to get to the point where we're going to need that information. But also, we talked about the fact that a simple harmonic oscillator has a period, the time it takes to oscillate. And we said that there's another way to describe that, and that's frequency. Right, we talked about that a little bit yesterday. Now, frequency and period are related. They are just different ways of measuring the same thing. So frequency is the number of oscillations per second, while period is the number of seconds per oscillation. Do you see that they're inverses of each other? So frequency is just 1 over the period. In fact, we tend to use frequency for things that oscillate fast, and we use period for things that oscillate slow. And that's because they're inverses of each other. So if something has lots of oscillations every second, you would probably describe it using frequency. But if something takes a long time to oscillate once, you'd probably use something like period. So I wouldn't use frequency to describe the moon going around the earth, right? It takes 28 days. Its period is a long time. But if I wanted to talk about like the beating of a hummingbird's wing, I'd probably use frequency because it does a lot of beats per second. Does that make sense? They're the same. They're really saying the same information to you. It's just that it's easier to talk about frequency with things that oscillate fast, and it's easier to talk about period with things that oscillate slow. That's why we have the two measurements. But, and this is important, we have different units for them. Period is seconds per oscillation, but the word oscillation doesn't have a unit associated with it. It's an idea when something repeats. So seconds per repetition, right? I wouldn't put there's no unit for that. So period is measured in seconds. But frequency would be measured in oscillations per second. So the unit of frequency is 1 over seconds. And that has its own unit called the hertz. So anytime you've heard something like megahertz or gigahertz, it's referring to a frequency. So radio waves, they're megahertz, and kilohertz, those are radio waves too. Your phone uses a similar form of megahertz to transmit its signal back and forth to the tower. It's just something that's oscillating. So anytime you hear hertz as something that's being used as a unit of measure, something is oscillating in that system. So if your phone, megahertz is the number of times the electrons oscillate inside the antenna. So there's lots of antennas in your phone. It's oscillating electrons. That's how it's sending a signal. That's how it's receiving a signal. Now, with that, I want to get into this picture here. This picture represents one portion of an oscillation. And we started talking about this yesterday, and the first thing I recommended that you did was identify in your oscillation where equilibrium is by drawing a line kind of indicating the equilibrium position. And I tried to also say to you, and I hopefully successfully yesterday, that this top one really just represents the at-rest system. What would happen if you just had the block connected to the spring, but you didn't give it any energy? You didn't pull it outwards and release it. If it was at rest, this is what it would look like. The velocity would be 0, the force on it would be 0, and the energy in the system would be 0. This represents the at-rest system, where the system would naturally be after all the energy has been drained from it. But then what we're going to do is we're going to take and pull outwards on the box and let it go. Now, to be very frank with you, I didn't put one complete oscillation in here on purpose. It'd be pretty redundant. So I put instead, if this represents t equals 0, the point where we pulled it out and we've just let it go, here to here is how much of an oscillation? It's half of an oscillation, right? I did not put the trip back. I just put the trip away. So if this was a pendulum, they swung away, but they still have to come back. Does that make sense? So this wouldn't be one complete period, this would represent 1/2 of a period, right? The trip back would be the other half of that period. Now, there's a few little things I want to throw out before we get started. I want you to know different things about each one of these stations, but I also want to recognize something from the onset, that although we're going to label a lot of these, there's going to be some takeaways at the end that are important and valuable, and I'm going to circle the things that I need you to kind of take away and kind of add to your notes as being special, because some of the stuff isn't particularly special, but some of the stuff is. So what we're going to do is we're going to take a look at what's happening in an oscillator at every one of these steps. And I want to describe several specific things about each step. I want to describe energy, force, acceleration, velocity, and displacement. Okay, those 5 things. So energy, force, acceleration, velocity, and displacement. You're going to hear me talk about it a lot, so you don't have to write those 5 things down now, because every one of these, we're going to write those 5 things. But keep this in mind, we are talking about the spring mass oscillator because it's an ideal oscillator. What we learn from this oscillator, we will be able to use for all oscillators. We'll apply the things that we learn from this to every other kind of oscillator out there. So this one is the ideal system, and every other oscillating system is just like the ideal system. So let's begin with the first step. This part right here represents t equals 0. This is the instantaneous moment when I've pulled the mass out, and just as I've let go. If you could just snap a picture in time, the instant I've let go. So it hasn't begun to move yet. In fact, right now, the velocity of the object is 0 because it hasn't begun to move yet. But the object is displaced. We're going to call the displacement x naught because it represents the amplitude. When we pull this thing out and let it go, we are establishing what the maximum displacement will be. Maximum displacement is the amplitude. So the amplitude has a big part to play in all of this. And the reason is because of energy. One of the most important things about a simple harmonic oscillator is that the energy of the oscillator is going to be constant. Remember, the spring force is a conservative force. So unless something takes the energy out of the system, energy is going to be conserved. At this particular instant, there's no kinetic energy because the velocity is 0. But there is what kind of energy? Elastic. So 1/2 k x naught squared. That's the amount of energy at the system when we first start, because all the energy is in the form of elastic. Now, there is something important about this point. At this moment, we are at maximum displacement. The force on the object is based on Hooke's law. And in Hooke's law, it's k times x, but in this case, it's x naught. Since this is the maximum displacement, this also has to be the maximum force. So this is the biggest the force is going to be on the object. Right? Because force is based on displacement with the spring. And since the displacement's the biggest it's going to be, the force is as big as it's going to be. Now, just I'm going to write something off to the side because you're supposed to remember this, but this is an unbalanced force. So Newton's second law plays a role here. We know that the net force has to equal ma. Well, the only force acting is the spring force. So minus k x naught equals ma. If I do just a little bit of arithmetic, that means the acceleration must equal minus k over m. I'm sorry. Yeah, minus k over m. x naught. I just took this and divided both sides by m. Okay? Now, if you look carefully, m is going to stay the same as this thing oscillates, right? And k is going to stay the same as this thing oscillates. But x naught is at its maximum right now. So since x naught's at its maximum, the acceleration must also be at its maximum. Right? Because this is the maximum displacement. This is when we have the maximum acceleration. Now, keep this in mind. This is why we don't use springs to shoot people or animals. When you first let go, they feel the maximum acceleration and maximum force all at the same time. That's traumatic and can hurt you. So we don't use things like that. We let things gradually build up. Even things that you think aren't gradual, like if you've been on that cheetah hunt, or you've been on Velocicoaster, or you've been on Hulk, or you've been on Rock and Roller Coaster, all of those systems that shoot you forward, they don't do it instantaneously. They feel like they do, but there's a small ramping up at the beginning to make sure they don't hit you with all the force all at once, because that can be traumatic. Even so, they try to do it fast to try and give you a thrill, which is why they say put your head against the headrest. Anybody forget to put their head against the headrest anytime on one of those rides? You learned a valuable lesson, didn't you? You won't do that again, will you? Because when it smacks you into there, you're like, oh, I discovered something today. I should keep my head against the headrest, just like the sign says. Oof, Velocicoaster's rough. It's a rough one. All right, so let's keep going, okay? So the very next thing, we're going to move to the next stage. And the object has been accelerated a small amount now. It's been pulled a little bit to the left. It's been accelerating, so now we have a velocity. It's in the negative direction because the left is negative, but we are moving to the left now. And because of that, we are no longer at x naught, but we are moving, but we are now a distance x away. Our displacement is smaller than x naught. So we're in a positive x direction, but we have a negative velocity. And you can probably imagine we have an acceleration that's still this way because we have a force that is still this way. So the force is acting in this direction, and the acceleration is acting in this direction. But the force is less now because x is less. So we want to think about the force. The force is going to be equal to minus kx. But this number is less than this number was. So we have less force and less acceleration. We're still getting faster, though, because any acceleration means a change in velocity. So we're still getting faster, but we're not getting as fast as we were. The acceleration is becoming smaller. However, we have some velocity now. Because we have some velocity now, the energy in the system is different. Not a different value. The energy is now split up into two places. We have kinetic energy and we have elastic potential energy. Right? The energy goes two places. But if nothing took the energy out of the system, this still has to equal 1/2 k x naught squared. The total energy is the same. It's just now split up. Some is in the kinetic energy and some is in potential energy. But the energy itself stays constant. Now, what this probably means, if you look into the future a little bit, is that if you know what you started with, you can probably figure out how fast you're going depending on where you are. Right? If I say you're halfway to equilibrium, you could probably figure out how fast you're going if you know you're halfway to equilibrium. Does that make sense to you guys? It's just an equation, so you can plug stuff in. We did this kind of stuff first semester. We pulled something back against a spring and shot it, and we would talk about how fast is it going when it leaves the spring. Same idea here. You're just setting the energy at one place equal to the energy at another. This is a transitional moment, but eventually we're going to make it to here. We're back at equilibrium. At this moment, x equals 0, right, because we're at equilibrium, how much time has passed? What part of the period is this? Interesting, but that's out of context. That's okay. If this whole thing is 1/2 of the period, where are we now? 1/4, right. So we reach equilibrium at a time of 1/4 of the period. This is going to be important. They're going to ask you about time in these problems. And one of the things we can't use are motion equations because this thing doesn't have a constant acceleration. We'll have to find the time another way. But when we pass through equilibrium, we are at the 1/4 mark. Right? And we need to keep track of that. Eventually we'll get a full period through this, but we're at the 1/4 of the period mark right now. Because x equals 0, the amount of potential energy is also 0. Does that make sense? So all of the energy is going to be in the form of kinetic energy, which means we must be traveling at the fastest we're going to be traveling. Right, we've been accelerating all the way to this moment, getting faster and faster and faster and faster, but now all the energy is kinetic, and that has to equal the original amount of potential energy we had. Yep?
Why was there potential energy in the one above it?
Because we weren't at equilibrium, so the spring was still slightly pulled outwards, so some of the energy was still in the spring. Does that make sense? But now, because we're at 0, the spring's no longer pulled out anymore. All the energy has been moved to kinetic energy. Excellent, Emery. Excellent. We're going to keep going, though. Do you have enough juice in the old iPad to keep it going? 32 should make it to the end of class. We've only got 20 minutes left. I think we can do it. You ready to move on? Excellent. No, it'll be okay. You might need a ladder to go get it. You're pretty short, but if you need some help, we'll find a tall person for you.
Thank you, Ava.
I said a tall person.
All of my mom is tall. It's 1.6. You can't.
Be tall in your mind. Just real quick, I think it shouldn't be hard for you to figure out what the Vmax is going to be. Cancel out the 1/2, divide both sides by m, and then take the square root. And this tells you how fast you're going to be going at equilibrium. This is as fast as you're going to go. This is one of those things you need to start thinking about. This is going to be an important topic. It's going to come up again in a few minutes. But also, based on Hooke's law, the force equals 0 and the acceleration equals 0. We're at maximum speed, but there's no force on the object. There's no acceleration on the object. We are passing through equilibrium. All right? Ready to keep going? Because things change now. We're on the other side. And because we're on the other side, our displacement is now negative. Right? We're on the other side of the spring. So our displacement's negative. Again, for a few moments, as we move to the other side, because force equals minus kx, the force is now positive because the displacement's negative, which means the force is now this direction, even though the velocity is still this direction. Right, we're still moving to the left, but the force is now to the right. And if the force is to the right, the acceleration is also to the right. We're slowing down. Right, we know that's going to happen. We were going as fast as we were going to be going at equilibrium, but now during this part, we're going to be slowing down because we're making it to the other side. We're going to make it to maximum displacement on the other side in just a bit. So that means for this one moment, our acceleration is going to be equal to minus k over m times x. We're just somewhere in the middle. But because x is negative, a is positive. That's why the acceleration is to the right. Thinking about energy, our energy is split up again. We still have velocity, so there's still a little bit of kinetic energy. But the spring is compressed, so we have some of the energy in elastic. But the total energy still has to equal the same amount as we started with. This still is based on whatever that displacement was. That's where the energy went. This is obviously very much the same kind of stuff as we had before, except our forces are slowing the object down, not speeding it up. Which is going to bring us to this point, when we're at 1/2 of the period. We've been slowing down for a little while now, so now we've reached the point where our velocity is again 0. Because we are now all the way back where we started, but on the other side. We've made it back to maximum displacement. So this is still max displacement. Our force is going to be maximum, but in the other direction. So this is going to be F max. And our acceleration is going to be maximum too, A max. And you should remember, because we're at maximum force, which means maximum acceleration, that acceleration is going to be equal to minus k over m times x naught. Because we're at the maximum acceleration now. Again, this is one of those things I need you to be thinking about. This is a seminal and important point. But all of our energy is now in the form of elastic potential energy. And it is the same amount that we started with. Now you guys can see from here that this is going to repeat itself, right? The spring's going to start pushing it back the other direction and get us back to our original starting point. This represents 1/2 of what's happening. And please notice, this is an exchange of energy, right? The energy starts as potential and then moves to be kinetic, then moves back to be potential. It's oscillating back and forth. The energy's oscillating too. The energy's changing forms, but it's oscillating. That's what an oscillator does. If there's nothing to take the energy away, this takes place forever. If something starts taking the energy away, what happens is, in this case, friction. A force that will slowly bleed the energy away. That's going to make x naught become smaller and smaller and smaller. And if x naught becomes smaller, the maximum speed becomes smaller, the maximum acceleration becomes smaller, and the energy becomes smaller. But notice, all of these things are based on K, M, and X. They control the oscillation. Now, you have all of this information, and it's telling you stuff about where the energy is, where the velocity is, when it's a maximum, when it's a minimum. So I need you to know, if I say, when is the energy all kinetic? You'll need to be able to say, at equilibrium. When is the energy all elastic? You need to be able to say, at maximum displacement. These are kinds of things I want you to know. You'll need to know when the force is at a maximum, when the acceleration is at a maximum, when the velocity is at a maximum. Okay? Simple stuff. You have it all right here. But let me just, over here, let's distill some of the things into one place. Vmax. It was the square root of K over M times x naught. Amax. It was K over M times x naught. I know I've left a negative sign out of both of those. It's because I don't care about the direction right now. I just want to give an idea of what is the maximum speed, how would you find it? What is the maximum acceleration, how would you find it? Now, the next thing I'm going to do is going to involve you guys a little bit, but it's also going to have to involve a bit of a leap of faith. We can't use Galileo's motions equations to describe this. And there's something missing, something that we need. We need to be able to describe what the frequency or the period is. We need that. Because like with anything else in motion, when something happens has been a pretty important part of this year. Right? How often have you had to figure out how long it takes for something to happen in here? It's a pretty important part, but we can't use any of our motion equations because this thing has an acceleration that's always changing. But what does the simple mean in simple harmonic motion? That's right. So we know that x as a function of t should be able to be modeled by either using the sine function or the cosine function. Now, I'm going to be straight with you. On Monday, you're going to be doing a lab. And in that lab, you'll be able to prove that our oscillators are sinusoidal. So you'll be able to prove it. I can't derive it for you, though. And the reason I can't derive it for you is it takes calculus to do so. And you guys just don't have the chops for it right now. Mechanics doesn't have the chops for it. Because, to be honest, this is something that requires the solution to a second-order differential equation. A lot of words in there you probably don't know the definition of. But it's important that you understand that there is a mathematical way to predict this. Do you remember at the beginning of the year, we predicted the Galilean motion equations? We did it by looking at graphs. Do you remember? Found the area under the graph and the slope of the graph, and from that we derived a couple of functions for things that had constant accelerations. And that's where the Galilean motion equations came from. But we were able to derive it from mathematical things that we measured in class. I'm not going to be able to do that as easily here. So I'm just going to tell you what the answer looks like, okay? But one of these is the right one, and one of these is the wrong one. And I'm not sure if you're going to be able to tell me which is which. So let's see. This is what they are going to look like. You know enough to realize that the cosine function and the sine function look exactly the same. So why would I want to use one of these versus the other? Can somebody come up with a reason why one of these might be better to use than the other one? You can go. Why don't you give me an idea? What do you think? So did our oscillator start at equilibrium, or did our oscillator start at maximum displacement? So which one of these would start at maximum displacement, sine or cosine? That's exactly right. The one we're going to use as our model is the cosine function, because it starts at maximum displacement. Most of our oscillators require us to move it to maximum displacement and release it, so the better model for us is the cosine. Excellent work. Now, this next part I can't prove to you either, because it does take it does take calculus. But there's a way to figure out each of these. And the process is called the derivative. And those of you who are going to take calculus are going to learn all about the derivative eventually. So who's in calculus now? All right, so you guys know how to do this. So you can keep me on the right track. And I'm not trying to call you out. You know that when you take the derivative with respect to time, there's a process. And it relates cosine and sine together. But it needs one more thing. It needs a rule called the chain rule for this particular example. So I'm not going to go into all of that. You'll have to take my word on it. But if you take the derivative of the position, you get the velocity. And what it's going to look like is this. Forgot to put enough room for the negative sign. There. Now, you brought it up, so I think it's important for me to kind of reinforce this. When time equals 0, cosine is at a maximum. That's why cosine is our starting part for position. But at time equals 0, sine is 0. Look back at your page. What was the velocity at time equals 0? 0. That's why sine shows up for velocity, because it's at 0 at time equals 0. All right, to get the acceleration, we have to take the derivative again. Again, I know you don't know what that is, but some people in the room do. And when you take the derivative, again, you get a function that looks like this. Now, at time equals 0, cosine is at a maximum. Now, look back at time equals 0. Was the acceleration at a maximum on our little chart? But also it says the acceleration was negative at time equals 0. And our little chart, was our acceleration negative? Right, it was to the left, wasn't it? And to the left was negative. That's because we pulled the thing out to the right, so the acceleration had to be to the left, because it's a spring. So our motion equations at least work for time equals 0. They say the things we want them to say for time equals 0. But this part's important. At the very beginning of class, I asked you guys, how long does it take for the function to repeat itself? And Emery delivered us the answer when this increases by 2 pi. In fact, what she told us is we just got to take 2 pi and divide by b. And that gives us our answer, right? Okay. So period is 2 pi, but we're going to divide by square root of k over m. So instead of dividing by it, I'm just going to flip it, put the square root of m over k. Okay? Now, frequency is 1 over the period. So if I just take the frequency function and flip it, if I take the period function and flip it, I get the frequency function. So 1 over 2 pi, and I'll just flip the inside here, k over m. Now, this part's super, super important. Do you notice that all of these have k over m in them? It is, and that's the point. All oscillators are going to have something like this that controls the motion of the oscillator. Look at where it is. It's in every one of these equations. And it tells us that that's going to be controlling the system. In every one of these, k tells you what the maximum speed is going to be, and m tells you what the maximum speed is going to be. It's limited by those two variables, and how far you pull it out to begin with. Same with the maximum acceleration. It's going to be limited based on the spring, the mass, and how far you pull it out to begin with. The frequency, the spring and mass makes a difference. It determines how fast it's going to oscillate. Same with the period. Look, we talked about it yesterday. When the thing was heavier, it took longer to bounce, right? We saw it in class. When the thing was heavier, it takes longer to bounce. That's exactly what this says. It comes straight from these functions. Because this term shows up in all of these, there's a term like this for every single oscillator, and we've given it a name. The square root of k over m is known as the angular frequency. And every single oscillator is going to have its own thing that controls this. In fact, there's a symbol that's going to be used for it, and you're going to love it. It's a symbol you already have, omega, because the angular frequency is in radians per second. If you work out the units for this, you will find that it's in radians per second. Every single oscillator has its own thing. So, this is going to be a little bit trippy. Don't be mad. But we can rewrite all of those in terms of omega. For example, V max is equal to omega times x naught. A max is omega squared times x naught. Period is 2 pi divided by omega. Frequency is omega divided by 2 pi. For our motion equations, x equals x naught times the cosine of omega t. V equals minus omega x naught times the sine of omega t. A equals minus omega squared x naught cosine omega t. Now I know it's a lot and it feels overloading, but every single oscillator, all you have to know is what the omega is for that oscillator. and you know everything about how the function works. For a spring mass, square root of k over m. You guys did a pendulum already. Omega for a pendulum, square root of g over L. Once you know that, all of these things about the motion you know. So all simple harmonic oscillators, anything that oscillates, a hummingbird's wings, like I said before, or the moon around the earth, anything that oscillates can be described by all of these functions. They describe everything about it. So if you ever want to know how long it takes something to happen, you just got to figure out what the omega is. And you just plug it in and you have that function. Now, I know that's a lot to lay on you, and I promise you, it sounds way more complicated than it is. What you're going to have to come to grips with is sometimes you're going to ask questions like, how long until it passes through equilibrium? You need to be able to look at that picture and know that, well, that happens on the quarters. Right? 1/4 of the time it's going through equilibrium, and then at 3/4 of the time it's going through the equilibrium. Right? It's always going to go back. When is it going to be at the maximums and the minimums? I was like, when is it going to be at the maximums? Well, it happens at time 0. It happens at 1/2. It happens back when we get back to the start at 1 full period. It happens again at 3/2. Those kinds of things, it's always going to be based on that, but there's only a couple things to actually know.